Hello everyone. Today we are going to be looking at some compound circuits. But I'm going to show you here some examples of some compound circuits. Here is our first one. In this one, you can see that I have a light bulb here and two light bulbs here. I kind of tape things down so that you can see the organization a little bit here. These two light bulbs, you'll notice, are in series with each other, while this light bulb here is in parallel with these two. I'm going to go ahead and flip the switch, and I want you to see what comes on. When I flip the switch, you can see that this one turns on, and it burns significantly brighter than these two little ones, which are in series with each other and in parallel with this one. Now, here's another circuit. Wait for it. Wait. Can you see all of it? I feel as though you cannot. Sorry, team. Okay, there you can see it all. So in this circuit here, we have one light bulb here. This light bulb is on the path back to the battery, and it is the only path back to the battery. Check your paths. You could either go from here through this first light bulb and then through the second light bulb back to the battery, or you could go from here through this light bulb but then through the second light bulb back to the battery. So all of the current always has to flow through the second light bulb. That means this light bulb is in series with these two light bulbs here. Let's go ahead and turn it on. And here's what you should see. You should see this light bulb glowing very brightly, and then these two, very, very hard to see. But if you look very closely, they are glowing just a little bit there, but significantly less than this one. These are both types of what we call compound circuits because they have both series elements and parallel elements. And that's our topic of the day. I'm going to pause this video. I'm going to go ahead and get things set up here and turn on the lights and all that good stuff, and then we'll be ready to go. One sec. Okay, and we are all set to go here. We are going to talk about compound circuits today. When we say compound circuits, we mean circuits that have both series elements and parallel elements. And we're going to learn how to analyze these compound circuits to find the current in different parts, the potential difference in different parts, and the resistance of different parts. Now, compound circuits really are some of my favorite kinds of problems because they're very, very puzzly. What will happen is that you'll have one part that you get stuck on, and then you can find one little piece that fits into place, and then that allows you to find the next little piece that then allows you to find the next little piece, and so on and so forth. So they're really going to be kind of puzzly, where you're going to be finding little bit by bit by bit by bit by bit to try to solve the circuit. We're going to start with one of the compound circuits that you just saw, and I'm going to draw it right here. We had a battery. This battery was connected, this battery was connected to a little resistor here, little light bulb situation, like this. And then it was also connected to another resistor here and another resistor here, like this. Oh, I'm so sorry. Miss Wilson, let go of your need for perfection in your lines. They get the gist. They understand the idea that you're going for. Okay, here we go. So when we make any of these diagrams, anytime we make a schematic diagram, we always label the direction of the current. We always label the potential difference of the battery. We always label our resistors. I'm going to call this one R1. I'm going to call this one R2. And I'm going to call this one R3. Notice that we have two different paths back to the battery. Whenever you're analyzing compound circuits, you've got to keep thinking paths. If things are on the same path as each other, they're in series. If they're on different paths, then they're in parallel. If you look at this circuit, R1 and R2 are on the same path back to the battery. So R1 and R2 are in series with each other. And those two are in parallel with R3 because R3 is on its own independent path back to the battery. The first thing that we can do is we can find what we call equivalent resistance, and that will unlock the key to solving any other part of this circuit. When we find the equivalent resistance, we're looking for the total resistance of the whole circuit. Now, I told you last time that equivalent resistance is basically the same thing as finding the total resistance. Well, really, equivalent resistance, and I said this last time in the last video, but you can think about it as if I were to replace R1 and R2 with one resistor that had the same resistance as R1 and R2 do together, combined, that would be the equivalent resistance of R1 and R2. If I want to find the total equivalent resistance of the circuit, then I'm looking for a resistor that I could use to replace R1, R2, and R3 that would basically have the same resistance of all of them combined in the setup. To find the equivalent resistance, I start with a conceptual statement of what is in series with what and what is in parallel with what. A little bit of notation here. We use a comma for things that are in series. So for this, I would say that the equivalent resistance is equal to R1 and R2 are in series with each other. I draw a little comma to represent that they are in series. To represent that these two are in parallel with R3, we use a double slash to show parallel. I'll show you what we mean here. I'm going to say that these two are both in parallel with R3. This is a statement that I will always make before I actually do any math. So I always start by saying these are in series. I put a comma between the things that are in series, and then I put a dashed line between the things that are in parallel. Notice I have to have parentheses around R1 and R2 here because R1 and R2 both are in parallel with R3. It's not just R2 that is in parallel with R3. It's not just R1 that is in parallel with R3. It's R1 and 2 that are in parallel with R3. Now, after writing this statement, I can turn this into math. Here's how I do it. Anything that's in series, I just add together. Anything that's in parallel, I do 1 over that thing plus 1 over the other thing, and then 1 over all of that, as we are accustomed to doing. So, for example, here, to find the equivalent resistance of just R1 and R2, I'm going to add them together. I'm going to say R1 plus R2 gives me the equivalent resistance of this branch. Now, this R1 and R2 functions, I can kind of treat it like its own little resistor here. Like, sorry, I want to highlight with some colors here. Oh gosh, but not like that. Wow, wow, wow. Wow, wow, wow. Okay, this little statement right here represents this little branch right here. Now, if I want this little branch to be in parallel with this little branch, I want this whole statement to be, whoa, I'm going to switch back to my other color. I want this whole statement to be to the -1. The reason why I want this whole statement to be to the -1 is because I'm going to add it to R3 to the -1 and take this whole thing to the -1. The same way that if we were in parallel, I would do, like if I just had like this branch, if I just had R1 and R2 here like this, then I would do R1 to the -1 plus R2 to the -1, and then that whole thing to the -1 to show things are in parallel. Here I'm doing the exact same thing. It's just that this is made up of 2 resistors right here, this part that's in parallel. And now that I have this statement, I can go ahead and plug in numbers. In this case, let's say that all of these resistors are equal, that R1 is equal to R2 is equal to R3, and we'll say that they're all equal to R. Well, then we can do a little bit of simplification here. This would mean that I have 2R to the -1 plus R to the -1, and all of that here to the -1 like this, which I can flip these upside down and get rid of these little negative signs here if I want to, and I can call this 1 over 2R plus 1 over R, all of that to the -1. Now, oh gosh, okay, move please. Now, at this point, I can combine these two fractions, so this would be like 2 over 2R, and I get 3 over 2R, all to the -1. The -1 just means flip this thing upside down, and when I do, I get 2/3 R. And that is the equivalent resistance of this circuit. A few things to note here. First, because I just want to like point out a few things that are going to help us solve the next circuit. So I'll do that in purple. Right here and here, sometimes I like to choose points on a compound circuit and label them. I'll label this one A and this one B because I can show different things between these points. Do you agree that between points A and B, the potential difference is V naught? So across this third R3 right here, the potential difference across R3 is V naught. That also means because this end of resistor 1 is connected to A and this end of resistor 2 is connected to B, that also means that the voltage drop, the potential difference across R1 and R2 is also equal to V naught. So you have the same voltage drop here as you do here. Now, what we saw in that, one like little clarification here, that does not mean that this potential drop right here and this potential drop right here are V naught. It means that this potential drop plus this potential drop together equals V naught. A little bit of a note about the current. The current here, because all of these resistors are equal to R because they all have the same resistance, if you were a little electron and you could choose to either take a path through one little toll booth right here or through two little toll booths right here, you would probably choose to take the path through one little toll booth instead of two. And so most of the current will flow through this first branch, but some of the current, a little bit less of the current, will flow through the second branch. We get, because this resistance is twice as much as this resistance, twice as much current will flow through this side as will flow through this side. So I3 is going to equal twice as much current as the current that flows through I1 and 2. And isn't the same current going to flow through both because they're in series with each other? Okay, now that we've tried one that's a little bit simple, I think we're ready for something a little bit more challenging. Go ahead and take your textbook and open up your textbook to page 662. If you look on page 662, you will see a beautiful picture of a circuit. I'm going to do this circuit in green. You're going to see a beautiful picture of a circuit that looks kind of, okay. Bye. That looks kind of something like this. I have a battery here, and it says that the potential difference of my battery, delta V naught, is equal to, oh no, not that, please. I did this bad. Okay, wait, I'm going to scooch all my work over. So sorry, team. Okay, here's my battery. The potential difference of my battery is equal to, it says, 14.0 volts. Then I have a resistor right here that's connected to a little point here. Then it's connected to another little resistor right here. Then it's connected to another little resistor right here. Then this is connected here to another point over here. This goes up. We got another resistor here. And we got another resistor here. And we got another resistor down here. And, then this connects back to here. Then this connects over here on this side and then comes back to the battery. We got a lot of things that are labeled on here. This is RA up here. RA, it says, is 5.0 ohms. This is RB right here. This resistor is 7.0 ohms. This is RC right here. It is 4.0 ohms. This is RD right here. RD is equal to 4.0 ohms. Then you have RE right here, which is equal to 4.0 ohms. Then you have RF down here, which is equal to 2.0 ohms. Last things. last, we label our current and we say that I naught is going to go around this whole circuit this way. Wow, this is a crazy looking circuit, but what's going to be even crazier is all of the things that we are asked to find. Are you ready? Here's our list of knowns and unknowns. We are looking for the potential drop across A. We are looking for A, the current through A. We're looking for the potential drop across B, the current through B. We're looking for the potential drop across C, the current through C. We're looking for the potential drop across D. Oh gosh, move, please. Oh, sorry, so sorry. Okay, we're looking for the potential drop across D, the current through D. We're looking for the potential drop across E, the current through E. We're also looking for the potential drop across F, the current through F, and that's it. All of these things are the things that we're looking for. Okay, now this is going to be a very, very puzzly problem. We are going to start by finding, always, whenever you have one of these kinds of problems, the first thing that you're going to do is find the equivalent resistance. Once you find the equivalent resistance, you are going to be ready to start working through some other things. We'll find the equivalent resistance, and then, like I said, this is going to be kind of a puzzly sort of problem, where you find one piece, and that unlocks the secret that allows you to find another piece, and that unlocks the secret that allows you to find another piece. So, let's go ahead and get started here. I'm going to start by finding the equivalent resistance. Here's how I do it. I'm going to look at different branches here and see what I can simplify. To me, I like to start with the most complex sort of stuff. Here's what I'm going to say. Okay, got to move this out of the way once again. Move down here, please, and thank you. I'm going to start by saying, okay, it looks to me like RA and RB are in series with each other. Those together appear to be in parallel with RC, because if I were a little electron, I could take two different paths. I could take a path through RA and RB. They have to be in series because they're on the same path. Or I could take a path through RC here. So these two are in parallel with RC. Now I have effectively simplified this little spot right here between these 2 points, which I'll call point 4 and point 3. I'm going to actually label those in different colors because I think that's going to end up being helpful later. 1 second, team. Okay. Here we go. Between points. Okay. So sorry. You guys are like, could you just not label things in different colors? Okay, between 3 and 4 here. So now I have effectively, do you see that I have simplified down this whole expression is for R3 and R4. Or, sorry, is for the path between 3 and 4 has now been simplified down into one little thing. Now I'm going to tackle this next little section here. This next little section, I'm going to go with a green still. I don't know how I feel about that. Perhaps with a light blue. Okay, we're going to go with a light blue here. Next, I'm going to tackle this little section that's between here and here. Here I have point 2 and here I have point 1. To simplify this, I see that if I'm on my way from the battery back to the battery, that I can either take a path through RE or I can take a path through RD. So that tells me that RE and RD are in parallel with each other because they are not on the same path. So I'm going to write that RD and, whoa, not that, and RE are in parallel with each other. And that simplifies down this part right here. Wait for it. That simplifies, oh gosh, okay, yep, totally. We love when it just draws random squiggles all over the page. Okay, that simplifies down this path for us, so now we've simplified down this branch. And then finally, all of that seems to be in series with RF. Do you see how no matter what, I'm gonna have to go through RF to get back to the battery? There's no way to do this circuit without going through RF. Why are things like crazy here? Do you guys see that line? That line is insane. It's wild. And how come I've lost my pen capabilities? Okay, one second. I'm going to pause and get my technological issue sorted out. Okay, so what you should see, thanks for your patience. You actually didn't have to wait at all, but that did take me like a good second. Okay, what you should see here is that no matter what, all the current has to go through RF. There is no path back to the battery that doesn't involve me going through RF. So RF is going to be last here like this. Now, do you see that all of this chunk right here, this 3-4 chunk, and all of this 1-2 chunk, I like to call them branches, all of the 3-4 branch and all of the 1-2 branch is in series with each other. Like, I have to go through the 3-4 branch, and I have to go through the 1-2 branch, and I have to go through RF in order to make it back to the battery. There's no way to do this where I'm not going through some part of the 3-4 branch, where I'm not going through some part of the 1-2 branch, and then making it back to the battery. So these are all going to be in series with each other. Now, in order to show this correctly, I do need parentheses around each of my branches to separate them from each other, and this is my final expression for RE. That's the equivalent resistance of the circuit. Now, next, to do this, I'm going to turn this statement into math. And the way that I'm going to turn it into math is anything that's in series I'm going to add together, and anything that's in parallel I'm going to do 1 over that thing plus 1 over the other thing and then 1 over the whole thing. So I see that RA and RB are in series with each other, so I'm going to add those together. But then those two together are in parallel with RC, so I'm going to write this like this. That whole thing then needs to be to the -1 because it's all in parallel with each other. That then I go to the next one. I'm going to do RD and RE. These two are in parallel with each other. It's a much simpler expression here. I just do 1 over RD plus 1 over RE all to the -1 like this. And then finally I have RF. I add each of these together like so, because all of them are in series with each other, so I can just add them all. Now I can plug in numbers. I plug in for RA, I plug in 5.0 ohms. For RB, oh gosh, wait, don't parenthesis yet. Okay, for RB, I plug in 7.0 ohms. For RC, I plug in 4.0 ohms. I'm going to be mindful of my space here. We're about to run out of it. For RD, I plug in also 4.0 ohms. For RE, I plug in 4.0 ohms. And then lastly, I plug in RF, which is 2.0 ohms. You can plug that into your calculator, and when you do, you should get a number like 7.0 ohms. And that is the total resistance of our circuit. Now, this is going to allow us to unlock all kinds of things. So the first thing that I always do is find RE. Almost always the second thing that I'm going to do is I'm going to find I naught or delta V naught, whichever one I don't have. So here's why it's really easy to find I naught, is because I naught is going to equal delta V naught over the total equivalent resistance. Now I have the total equivalent resistance, so I can just plug in 14 volts divided by 7.0 ohms, and I get that the total current through this thing is 2.0 amps. Lovely, nice and easy. Now here's one of these things. This actually wasn't an official answer, so I probably shouldn't box these because it's not one of the things that it asked me to find. Though I am going to circle both of these things because they are going to be super relevant to me. In these problems, I do recommend, and this is one of these few problems in this class where I recommend this, but I do allow on these kinds of problems plugging in numbers before you get to your final answer. You can plug in to find your equivalent resistance. You can plug in to find I naught. You cannot plug in up here like to find the resistance of, to find the resistance of this branch or to find the resistance of this branch. Once you have a final algebraic expression for RE, you can plug in a number. Once you have a final expression for I naught, you can plug in a number. that's really the only case is like one of these sort of situations, one of these kind of compound circuits where you're going to plug in numbers before you're getting to your final answer, because what you're going to see is each little answer will unlock the next answer. Okay, so now we have RE and we have I naught. We are now ready to begin our journey to find everything else. I like to start with things that are really easy to find. So I always am just looking for like what's the easiest next thing to look for. For me, when I'm looking at this circuit, I think that the easiest next thing to look for is going to be IF. And here's why I think that is because isn't the total current in the circuit all going to flow through RF? So that says to me that if the total current is flowing through, then IF is going to equal I naught. Another way to think about this is that RF is in series with everything. And if it's in series with everything, then it's going to experience the same current as everything else. Here's the truth, is that the current's going to flow through here. All of it's going to flow through IF. It's going to get to point 1 and it's going to split. Part of it's going to go through RD. Part of it's going to go through RE. It'll join back up at point 2, take the rest of its journey all together. Then when it gets to point 3, it'll split up again. Some of it will go through RA and RB. Some of it will go through RC. Then it will join back up again at 4, and all of it will flow together. But do you see how all of it flows together through RF? So the next thing that I'm going to find is IF. And this is going to be very easy because IF is just going to equal I naught, which is 2 amps. I'm actually going to write this down on the next page here, or you know what I'm going to do? I'm going to pause the video so that you don't have to watch me. I'm going to erase all of this stuff here and just leave the important stuff, and then I'm going to write down my new information. One sec here. Okay, so now here's what I know. I know RE is equal to 7.0. Whoa, volts or ohms. That is crazy that I put ohms for both of those. That is just embarrassing. Wait for it. Wait, not that. Okay. Sorry, move this up here. Okay, I know that RE is equal to 7.0 ohms. I also know that I naught is equal to 2.0 amps. Okay, that's much better. Now, here's what I learned. I learned that because all the current is flowing through IF, or flowing through RF, excuse me, then I'm going to move this back down here. So sorry. Okay, it's just all a process, people. That means that IF is going to equal I naught, which is going to equal 2.0 amps. And there it is. I found one of my things. Yay. Now I look at my list and I say, okay, what's going to be the next easiest thing to find? And I say, to me, it looks like the next easiest thing to find is going to be delta VF. Very, very simple. I got delta VF is equal to IF times RF. I already know what IF is. IF is 2.0 amps. I already know what RF is. RF is 2.0 ohms. And so then when you do that in your head, you get 4.0 volts for delta VF. Great. There's another one. Now as I'm looking at this circuit and I'm trying to decide what's going to be the next easiest thing to find, I'm thinking branch 1 and 2 is going to be the next easiest to analyze after RF. So let's take a look at branch 1 and 2. I will switch my pen color to blue here to talk about branch 1 and 2. When I'm looking at branch 1 and 2, here's what I'm looking at. I'm looking at two resistors here that are both in parallel with each other. I know that they're in parallel because if a little electron got to here, it would have to make a choice. It could either go through RD or it could go through RE. Those are on two different paths. And so I say because they're on two different paths, then they must be in parallel with each other. Okay, now there are a few things that I know here. I know that when all of the current I naught gets here to point 1, it's going to split. And some of it is going to go through D and some of it is going to go through E. So I have an equation here that says that for things that are in parallel, you add together their currents to find the total current. I naught, when it gets to 1, is going to split into ID and IE. So that's one thing that I know. Here's another thing that I know. Because RD and RE are in parallel with each other, let's follow parallel rules. That means that delta VD is going to equal delta VE. since they're in parallel with each other. The voltage drop across E has to equal the voltage drop across D. Okay, I know that. And then there's actually one other thing that I know here. And the last thing that I know is that just looking at this, RE happens to be equal to RD. Now, this is not always true, but in this particular case, it happens to be true that they're both equal to 4 ohms. This is going to be very helpful to me because I know that ID is equal to delta VD over RD. And I also know that IE is equal to delta VE over RE. And if delta VD equals delta VE and RD equals RE, well then ID and IE are going to be the same as each other. This means that if ID and IE are the same as each other, I could just plug back in for IE. I could just sub in ID right here. So I would get that I naught is equal to ID plus ID. Or in other words, I naught is equal to 2ID. Or in other words, once again, ID is equal to 1/2 times I naught. Now this should make some sense to you. We know that this is both equal to IE here. Actually, I'm going to plug in numbers and then I'll talk about why it makes sense. When we plug in numbers here, we get to 1/2 times 2 amps. 1/2 times 2 amps is, of course, 1 amp. And so we see that the current through IE and the current through ID are both going to be 1 amp. Now, this should make sense to you because as all of the current gets to here, when all the current gets to 0.1, it's going to split. If I'm looking at these two options and I'm a little electron, I got one toll booth with a resistance of 4 ohms, another one with a resistance of 4 ohms. Hey, they're exactly the same. We got two paths. Doesn't that make you think that half of the current is going to go this way and half of the current is going to go this way? So if we are looking at this problem, we would say, oh, well, I naught is going to split and half of it will go this way through RE and half of it will go this way through RD. That means that ID is probably 1/2 of I naught and IE is also probably 1/2 of I naught. So I showed all this math here to show you kind of how you get to the answer, but you could almost do this entire thing instinctually, just saying, okay, wait 1 second, here's really the only things that you would need. You would need to say that these two resistances are equal to each other. Whoa, did not mean to mark there. You need to say that these two resistances are equal to each other. And then you'd probably need to say that you need to add these together to get the total. And then you could probably just jump to this and say, you know what, the current through D is going to be equal to 1/2 of the current through I naught. And the current through E is going to equal 1/2 of I naught. So that is how you find ID and IE. If we're looking at our list of things here, I'm trying to see what's going to be probably like the next, wow, I just can't make the check marks when I would really like to here. Okay, imagine there's a check mark over there. When I'm looking at this thing, I'm like asking the question to myself, what is going to be the next easiest thing to find? I see that I found IE and ID. So I'm thinking that the next easiest thing to find is going to be VE and VD. And I say, okay, that's going to be nice and simple here. And I'm going to erase some, oh gosh, not that. Okay, well, sure. That's great, but I actually want to go back. So thanks for that little detour. I did appreciate that. Way to go, me. Okay, so I'm going to erase some of my work up here. Boop, 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 boop. Sorry to all of my work for resistor F. Okay, so here's what I'm thinking now. I'm thinking that I know I and I for ID and IE, so then if I know the resistances, then I can find the potential differences. And so here's what I do. I say delta VD is going to equal ID times RD, which is also going to equal delta VE, by the way, and it'll also equal IE times RE. Well, here's the good news is that all of these numbers are the same. So for ID, I can plug in 1.0 amps. That's the same thing as IE. For RD or for RE, I can plug in 4.0 ohms. And then my final answer here, I'm going to get 4.0 volts. And that gives me both VE and delta VD. I've accomplished a good amount of this circuit here. I'm going to once again pause the video. I'm going to erase some of my work here. I'm going to write down the names of all the values that I found so far, and then we'll start working on the next part of the circuit. Okay, one sec. Okay, everything should be cleared out now. Here's a list of the things that I found. I found that delta VD equals delta VE, which is equal to 4 volts. I found ID and IE are both equal to 1 amp. I found delta VF is equal to 4 volts and IF is equal to 2 amps. Now we're ready to start conquering this little guy right here, branch 3 and 4. If I want to conquer this little branch 3 and 4 here, here's some of the things that I'm thinking. I'm thinking, okay, well, RF seems to be in series with this 1 and 2 thing, which seems to be in series with this 3 and 4 thing. I'm thinking they're all in series with each other. So that means that my potential drop across here, plus my potential drop across 1 and 2, plus my potential drop across 3 and 4, all together adds up to delta V naught. So that's going to be the first thing that I write down here, is I'm going to write down the delta V naught. Whoa. Oh gosh, guys, this thing is just the worst sometimes. Okay, move it down. Because if I get anywhere near it, then it's like, you want to click this, right? And you don't want your mouse to actually work. And I'm like, no, I actually do want my mouse to actually work as like a real thing. Okay, here we go. Delta V naught is equal to delta VF plus delta V for my little 1 and 2 thing going on here. Let's make that a little bit clearer. 1 and 2 plus delta V for my little 3 and 4 thing that I got going on here. Okay. So now I'm thinking, oh, this is interesting. I already know delta VF, so that's cool. And I also already know delta V1 and 2, because isn't delta V1 and 2 going to equal delta VD, which also equals delta VE? So I'm going to write plus delta V D and E, since they're the same. Then I'm going to look at this next part, which is delta V3 and 4. That's the only thing that I don't know yet. So I'm going to find this little one right here. And the way that I'm going to do it is I'm just going to rearrange and solve. I get the delta V for 3 and 4 from between this point here and this point here. That delta V is going to equal delta V naught minus delta VF minus delta V of D and E here. When I plug in numbers, I get the delta V naught is equal to 14.0 volts minus delta VF. Delta VF is equal to, where did I write it? Oh gosh, 4.0 volts. Minus delta V D and E, we just found, is also equal to 4.0 volts. Do it in my head, and I get that what's left is 6.0 volts is my potential drop across 3 and 4. Now you say, Miss Wilson, why would we find the potential drop between 3 and 4? Well, because check it out. Isn't the potential drop between 3 and 4 also equal to the potential drop across this resistor C right here? So here's what I get. I get that the potential drop across C is equal to 6.0 volts. And now didn't I just find one of my things? So I can go ahead and check that one off. What's the next easiest one to find? Did you say the current through C? I'm thinking the same thing. The current through C is going to equal delta VC over RC. Delta VC, we know now, is equal to, I gotta move my guy again. Okay, move out of the way. Thank you, buddy. Up here is a nice, helpful place for you to go. Okay. Oh, gosh. Okay. Oh, no, except now I can't access my undo button. That is the worst. Okay. Delta VC is equal to, what did I just say, 6.0 volts, divided by RC. RC is equal to 4.0 ohms. Try it in your head. You get 3 over 2, which is 1.5 amps. Done. Next, we're going to look for delta VA, IA, delta VB, and IB, which are all along this little branch right here. Once again, I'm going to go ahead and erase my work, write down my significant values that I found, and then we'll jump back in 1 second here. Okay, here we go. We got a nice clean slate here, and now we have all of the things that we have found listed down here. We found the potential and the current through this one. Potential and different here, potential and potential difference in current here, potential difference in current here, potential difference in current here, potential difference in current here. The last thing that we have to find is A and B. There are lots of different ways to do this. I'll show you 2 different ways to do this, but there are other ways that you could get this work done. So I'm going to show you 2 ways to do it. Here's the first way. Okay, so when I'm looking at this, I'm thinking, okay, here are the things that I already know. I already know that because RC is in parallel with these guys right here, I know that the potential drop across A and B together is equal to the potential drop across C. So I also know that resistances, here's one thing that I'm thinking, is I'm thinking I could talk about current here. I know that the current through A is going to equal the current through B since they're in series with each other, which is going to equal the total current for this whole little branch here going through both A and B. And I think, okay, if I wanted to find the current through the whole little branch through both A and B, what I could do is I could take the potential difference of the whole little branch, which is the potential difference between 3 and 4, and I could take the resistance of the whole branch, both A and B, and then I could solve that and find the current through both of them. So here's what I'm going to do. First, I know that delta V3 and 4 is equal to delta VC. I also know that RA and B, well, because they're in series with each other, that's going to be RA plus RB, like this. I can then plug in numbers here, and I'm actually going to plug in numbers up here, even though I'd normally like to work all the way down just to save us some space here. Delta VC here, I already know, is equal to, where's my list over here, 6.0 volts. And RA, I know, is equal to 5.0 ohms. RB is equal to 7.0 ohms. Sorry. Okay. Combine those two, and I get 6 divided by 12. That's 0.50 amps for my final answer there. So now I found the current through A and B. That's one way to find it. Let me show you another way. Another way that you could do this is you could say, well, RC is in parallel with RA and RB. So I know that the total current that's going into 3, which is I naught, is going to equal the current that goes through C plus the current that goes through A and B. To find the current that goes through A and B, here, I can do I naught minus IC. The current that is I naught, we already know, is 2.0 amps. The current that goes through C is 1.5 amps. And so I'm left with, here, 0.50 amps. Both of these ways are totally great ways to find the current. One way relies on the addition rules for current in parallel. The other way relies on Ohm's law and the total voltage through here and the total resistance through here and the fact that these are in series, so the current through the whole thing will equal the current through each one. Either way is a totally great way of finding the current. Now that I have the current, all that I have to do left is find delta VA and delta VB. So now to find the current, or to find the potential difference across A and B, I'm just going to use delta VA is equal to IA times RA, and delta VB is equal to IB times RB. I can plug in here, IA is equal to 0.50 amps. RA is going to equal 5.0 ohms. Then delta VB is going to equal, let's just give ourselves a little more space here. Okay, this is going to equal, I still want more space. Sorry, okay. IB is also equal to 0.50 amps. RB is equal to 7.0 ohms. Checking both, we get 2.5 volts here, and over here you get 3.5 volts. And you are done. Another way to do this one, by the way, because there are tons of different ways to solve these kinds of circuits, if you knew that delta VC is equal to 6 volts, and that has to equal the potential difference across A and B, and I found delta VA is equal to 2.5, then couldn't I find that delta VB is going to equal delta VC minus delta VA, since this potential drop plus this potential drop together have to add to equal this potential drop. So then I could do 6 volts minus 2.5 volts, and I should get 3.5 volts. Because I see the same number both ways, I look at my answers and I say, yeah, that does look pretty good. It seems like I've checked things out here and they all look pretty good. And wow, would you look at that? That is the entire circuit, people. We did it. This is your, these are your first 2 examples of compound circuits. What I hope you found today is that these compound circuits act a little bit like puzzles, where you can find one little piece and that allows you to find the next little thing, and that allows you to find the next little thing. The whole way through, all that we're doing is we're following our circuit rules for series circuits, and we're following our circuit rules for parallel circuits. And that really can get you around the whole thing. In our next video, we are going to try yet another practice problem together, but hopefully this one gets you started so that you're feeling pretty good about these things now. If you're not feeling good about them, please know that these kinds of things really just take practice. The more that you do them, the more that you'll say, yeah, okay, I think I'm kind of starting to see what I should be doing next. And that's our lesson on compound circuits for today. I'll see you next time for another compound circuit. Have a great rest of your day. Bye, good people.